Hello everybody, and welcome to section 2.3 on page 57. In this section we'll be talking about compositions of linear transformations, a way of combining two linear transformations into one. Okay, so let's start by reading this definition together. Okay, so let t go from v to w and u going from w to z both be linear transformations. We're going to define a new transformation called ut that goes from v to z, and it's simply going to be the composition of the two linear transformations together, u composed with t. That's ordinary function composition, okay, that you've already learned about in previous courses. Okay, and just to emphasize, when we write ut, that's representing u of t of v. That's going to seem maybe a little bit unusual at first. When you see ut, it looks like a product. It's really not a product, though. It's a composition in our context. Okay, and first note that we'll make here is that Theorem 2.9 in our book actually guarantees us that ut is linear. Okay, if we know that u and t are linear transformations, then so is the composition. Okay, I want to jump down to and just draw a diagram of this so you can picture what's going on with this function composition. So we've got one transformation t that's taking us from v to w, and then another one called u that's taking us from w to z. Okay, and the composition is just taking us from the beginning to the end. Okay, so you can picture ut as being that mapping there. Now, when you first look at this, you might think, did we write the u and the t in the wrong order? Okay, and actually we didn't, because remember, when you compose two functions together and substitute a number in, the x actually gets substituted into the g first and then into the f. That's the reason why this here is ut and not tu. So we did get the order right there. Okay, now what we'd like to do is to ask the question, what about the matrix of this composite transformation? What would the matrix of ut be? Okay, and that's what Theorem 2.11 down here is all about. There's a relationship between the matrix of ut and the matrices of t and u separately. Okay, so let's read this theorem and fill it in together. So let v, w, and z again be finite dimensional vector spaces with ordered bases alpha, beta, and gamma. Okay, and assume that t goes from v to w and u goes from w to z, just like in the definition above. Those are both going to be linear. And what we're going to do then is to write down an expression for this matrix, the matrix of ut, taking us from gamma coordinates, or I'm sorry, from alpha coordinates to gamma coordinates. Okay, well, to help us figure out how that matrix would look or how it would break down, what we can do is to draw kind of an analogous diagram to the one that we just drew, but this time for coordinate vectors. Okay, so if you imagine taking a vector u and v, there's a coordinate vector for it relative to the basis alpha. Okay, and then if you were to take the vector u and substitute it into the transformation t, we're going to get an output t of u and a corresponding coordinate vector for t of u, okay, which would be the coordinate vector of t of u relative to beta, the basis for w. Okay, and I'm going to just call that matrix A, so we can left multiply by that matrix A to take us from one coordinate vector to the other. Okay, and then similarly, we've got this vector t of u. We could substitute that into the transformation u and get an output and a coordinate vector for that output that would look like ut of u relative to the coordinates gamma. Okay, and then there's a matrix that we could multiply by that would take us from the beta coordinates to the gamma coordinates. I'll call it b. Okay, so the matrix that we're looking for, okay, the one that's sitting here, would be the matrix that takes us from this coordinate to this coordinate. The picture tells us that that matrix is going to be b times a. Okay, so what it comes down to then is, what are these matrices A and B? Okay, well, the diagram helps us to figure that out. A, for example, is a matrix that takes us from alpha coordinates to beta coordinates. So if we wrote it down, it would look like the matrix of t, okay, because that's the function that takes us from v to w, going from alpha to beta coordinates. Okay, and then similarly, the matrix B, which is sitting here in our diagram, that takes us from beta to gamma coordinates, and it deals with the linear transformation U. Okay, and so in a nutshell then, what needs to go in the blank here is this. Okay, if we kind of look at our diagram and pull it apart, the matrix of U going from beta to gamma, okay, and the matrix of T going from alpha to beta. Okay, and again, you might think about this a little bit more and convince yourself that we wrote those two matrices in the correct order based on this diagram. It may seem backwards at first, but if you think about how function composition works, that's really the correct order. Okay, so to summarize, this theorem, Theorem 2.11, gives us a way of calculating the matrix for a composition transformation if we can calculate the matrices of the two transformations separately. And we'll be using this theorem for the remainder of this section.